Okay. So, in this particular session, I will come back to what I had promised earlier, that is behavior of the system in static and quasi-static situations. To analyze these two paradigms, the best suited equation would be the last one that we have over here. The dispersion relation, if it is written in terms of the energy of the quanta and their spatial momentum, then in the limit when the wavelength of the photons tend to 0, in that particular limit, this factor pi of L can be shown to reduce to something proportional to number of charged particles per unit volume divided by mass of those particles square, and it is otherwise also known as plasma frequency. For a classical system, this pi L contributes to this equation by a quantity that is equal to plasma frequency square. So, the energy budget of these excitations are given by omega square is equal to plasma frequency square plus wave vector square. The situation is perfect in the sense 1 square is given by sum of 2 square, those are also perfect. So, no trouble is seen in the paradise. If we can set the wave vector to 0, we can see that the energy of excitation or minimum energy of excitation in this particular system is equal to the plasma frequency, and that is how the whole thing vibrates and the universe remains stable. But suppose the wave vector that you have considered here is non-zero, then you see that if the frequency of excitation is less than the plasma frequency square, the wave vector actually picks up a imaginary piece. Why should it pick up? It becomes imaginary, because on the left hand side we have omega square minus omega p square to be equal to k square, and since omega square is less than omega p square, the difference is negative. So, k is bound to be imaginary, and what it tells you is that the system, the excitations in the system does not propagate up to infinity, it gets damped by a length scale which is given by omega square minus omega p square, square root. So, this limit when omega is equal to 0 and k tends to 0 are the screening regime, and the regime where k equal to 0 and omega tends to 0, their stability or instability, unstable mode generating regime, that is how they are known. So, once we have the clear idea about how this analysis follows, we can now revert our attention back to the first two equations that we had started with. And if we introduce a simplifying notations to make these two equations more appealing, we see that these two equations are given by the equation 3 and 4 what we have here, that can be written in a matrix form as capital omega square I A and minus I A capital omega square, signifying that this is a Hermitian matrix, and since it is a Hermitian matrix, it has eigenvalues, those are real, and if the eigenvalues are real, in general there should not be any loss of energy by the process of energy dissipation. So, what are the possible solutions of falling from the determinant of the matrix? There are two given by equation 6 and 7. The symbol A here actually includes the correction that we had talked about earlier as pi p, and if we write the full form of capital omega, then you can see they are displayed in two equations right before us on the top. Omega square minus wave vector square minus the transverse form factor is it related to or is proportional to pi p, and the other one is negative of something called negative of A. Now, if we focus our attention to the situation 1, which corresponds to wave vector to be equal to 0 and omega tending to 0, that is if there is any damping or unstable mode associated to this system, we see that omega square is now equal to A plus pi t in one case, and for the other case it is equal to the difference between pi t and A. The first case that follows from equation 8 does not show any signal or sign of existence of instability or damping, but the second case shows that it might be possible, and it might be possible just on the basis of the strength of the magnetic field that is pervading the system. So, it may not be very out of place to call it an external field catalyzed damping. So, this is not a kinematical damping effect that one is talking about, and this picture can be captured once we actually have performed the calculations following the prescribed processes or procedures of the quantum theory and then analyzed it. The case situation number 2 is case 2, when omega is equal to 0 and k tends to 0. In this situation, there are two possibilities. In one possibility, one situation, and it is always screened because k is imaginary. But in the other case, it is not so obvious that it is always screened. It only depends on the size of the corrections. Those are coming from each individual pieces and their difference. And if the difference is positive, there is no screening. If the difference is negative, there exists screening. So, no signal propagates outside the system. To estimate or to pinpoint what is going to happen in which situation, we should rather have a handle on the values of this pi t and pi p that has gone into these estimates. In general, when one is in a high temperature state, then in that case, in those situations, the mass of the constituent particles can be neglected in favor of the temperature. And in a situation like that, what we have seen is the unstable mode or the damping mode or the screening mode clearly depends on the scale at which the temperature is operating. So, in extreme situations where the temperature is large compared to the constituent mass, or conversely in a situation where the chemical potential outweighs the mass, can be accessed only by calculations that goes over to this paradigm in a proper appropriate fashion. The third and the most important point of this discussion is to realize that when the energy of the excitations are larger than the plasma frequency or other terms, magnetic field dependent terms or other possible sources, then this particular 2 by 2 matrix that we have joining the parallelly propagating mode with the orthogonally propagating mode can be diagonalized by a unitary transformation, and the result of this diagonalization by unitary transformation will introduce us with two new dynamical variables. Those are combinations of a parallel and a perpendicular and two new eigenvalues of the matrix. So, each one of these two eigenvalues of the matrix, after this diagonalization, will give us two dispersion relations for each one of these modes, and their solution would represent the propagation of vibration into different normal modes. This whole thing that I have just now described can be encoded by the solutions that I have shown with the top two equations in the slide, and from their behavior, it should be possible to find out how the tip of the polarization vector actually executes motion in a elliptic or along a elliptic curve, and how we can estimate the ellipticity of the elliptic curve, or to the extent that this ellipse is tilted compared to the observer's x axis and things like those, the degrees of polarization, etc. So, to do that, first let us get the picture of the ellipse clear. You can see that if this particular angle actually becomes equal to 0, then there is no motion along this curve, it is only a motion along the major axis of the ellipse. So, to estimate these angles, we can make some mathematical transformations, like go to a new frame by rotating the original vectors E x and E y in some particular way, and then in the process decide or come across certain measures that will tell us the size of the ellipticity angle. What is important in this business is the relation of this newly founded ellipse in a rotated coordinates system with that of the same when the system was not rotated. And as you can see that they are related to each other by their amplitude of oscillation in an unrotated case, the angle of rotation and the phase that exists between these two perpendicular vibrations that were defined here by delta 1 and delta 2. This delta is a difference between these two differences. And once things are perfectly taken into account, then it is also noticed that there exists something like a invariance relation between the old system and the new system, that is the square of the semi major axis square and their sum and semi minor axis square turn out to be the same, and the ratio of the semi minor axis to semi major axis takes us to the definition of the ellipticity angle, and the polarization angle, that is what is the angle that the new ellipse makes with the original axis, can also be estimated. We should come to end this discussion by noticing that if we define the difference of the squares of the original semi major and semi minor axis of the ellipse, this can be related to the two angles, rather they are cosine of two angles, and these two angles are the ellipticity angle and the polarization angle, and two other similar such relations. I have termed them as S2 and S3, where this ellipticity angle and the polarization angle enter, and this quantity S0, its square is related to the square of all the three. These parameters, those have been introduced here as S1, S2 and S3, are also termed as the parameters of Stokes or the Stokes parameters, and are in use to find out the polarimetric characteristics of a signal that comes. However, they can also be obtained differently rather than the route that we have taken here from the solutions of the two normal modes of the coupled differential equations in presence of in a magnetized medium. So, that is something that we will explore next, and at the same time also try to see if these variables, those we have introduced just now, they are inert to the Lorentz transformations, or depending on the velocity or the angle of rotation of the observer with respect to the emitter undergo transformations. So, with this we would rather conclude this session. Thank you.